Hi everybody. Today we're going to be learning about two concepts in physics. The first is systems and the second is conservation of mass. So when we're trying to analyze what is happening with different objects in physics, instead of evaluating what's going on with every single object, we can group them into things called systems. And there are different types of systems that we're going to be talking about today. Conservation, the word conservation means, in general, to keep the same amount of something, right? That's how you usually use it in speech. In terms of physics, there are four main conservation principles of physics. These are laws of physics that cannot be broken, and they are kind of the big ideas that we're going to be talking about this year. So the first conservation principle that we're going to be talking about is conservation of mass. So starting with systems, a system is a way of separating an object or objects from everything else for analysis. And when we use the word analysis, what we really mean is we're trying to figure out what's happening to that object, and what sorts of things are influencing maybe the movement of that object or motion or position. So I've drawn a fairly simple system here. We're going to call it a boring system. It's just a purple box, and we know it's a system because it has a lighter colored or a thinner line box going around it. So we've got a purple box in the middle. We know it's a system because we have a line drawn around it. Now over on the right, we've drawn another kind of system. This system is a lot more complex. It has a lot more parts. A race car clearly has a lot more going on than a boring purple box. But there's a line drawn around it indicating that it is also a system, just a more complicated one. And you'll notice that one system is composed of a solid line and the other is circled with a dashed line. And that's important because whether the line is solid or dashed, it indicates two different types of systems that we're going to be looking at today. In a closed system, an object is completely isolated from everything that's going around it in its environment, and we indicate a closed system with a solid line around the object. In reality, the problem is that nothing is ever truly isolated from everything else that might be influencing it. So we may have a Hi-Chew candy, like the one here, and it looks all alone, but in reality, that Hi-Chew is probably sitting on a table, so it is feeling the force of the table pushing up on it from below, and it is pushing down on the table. So that Hi-Chew is not really an independent, closed system. In addition to that, the table is sitting on the surface of the Earth, so it is interacting with the Earth, and the Earth is interacting with it. And so we could say, draw a line around the Earth and call that the closed system. But the truth is that things are interacting with the Earth as well. So the Earth is part of the solar system, and so you're having interactions with the sun and forces from the other planets and moons influencing the motion of the Earth. But even the solar system isn't a closed system, because if you move out even farther, you've got stars and galaxies and the whole universe that is having an influence on the motion in our solar system. So in reality, the truly only closed system that we have is actually the entire universe. So it's nearly impossible to create a closed system in reality here on Earth because everything interacts with everything else. But for the purposes of understanding physics and analyzing things on a smaller level, we often pretend we are working with a closed system in order to separate things. So in contrast to closed systems, where we are pretending that an object is isolated and not being influenced by anything outside the solid line we've drawn around it, open systems are a little bit different. In an open system, outside objects can exert forces on the objects inside the system and can change their motion or position. Objects inside an open system can also move in and out of the system, so in and out of the dashed line that we draw around it. So if we have a candy bar and it is in an open system, so you can see the dashed line around it, outside forces can be exerted on this candy bar, such as the gravity of the Earth. The Earth is pulling down on that candy bar. The table that the candy bar is sitting on might be pushing back up on the candy bar. The candy bar can also move outside of the system and possibly end up getting eaten by my dog, Coatsy. But let's hope that doesn't happen. So we can look at the idea of conservation of mass using both closed and open systems. Right now we're going to start by looking at closed systems. So at any instant in time, the total mass of a closed system is constant. So the total mass cannot change inside this box with the solid line around it. So let's say we have a closed system that contains my dog and a Haichu. And my dog, let's say he weighs approximately 65 kilograms, and a Haichu is 0.0025 kilograms. So we have a total mass of 65.0025 kilograms. So if my dog decides he's going to eat that Haichu and somehow he leaves the wrapper behind because he's really smart, his mass may go up, so he's now 65.002 kilograms, whereas what's left of the wrapper is just the wrapper alone is 0.0005 kilograms. But what you'll see is that the total mass in that system stayed the same. Nothing came in or went out of our closed system. So the mass of the Haichu candy got added to my dog, but the total mass of the system stayed the same. So throughout the change that occurred, the total mass is still 65.0025 kilograms. We can look at conservation of mass using open systems as well. So in an open system, the mass may be changing, but you can track it as it moves in and out of the system. So the mass actually isn't being destroyed, it's just moving somewhere else. So things can come and go from an open system, and we can just track where it comes from and where it is headed. So for our example, we're going to be using frozen yogurt as our open system. And we're going to track mass as it comes in and out of the system. So we're starting with 250 grams of frozen yogurt in a cup. And it has a dashed line around it indicating that it's an open system. Now, right before we decide to eat the frozen yogurt, we decide we're going to get 20 grams of gummy bears and 30 grams of hot fudge and add them to our frozen yogurt. So we have added mass to this system, and now our total mass of the system is 300 grams. So we're going to gobble up this frozen yogurt and gummy bears and hot fudge, and which comes out to about, let's say, 230 grams of goodness that's going to go out of our system now and into our bodies. So it's not being destroyed. That mass is actually just transferred to somewhere else. It's being transferred to your stomach. And all we have left over now is just, an empty cup and some drips of frozen yogurt. So there's left over maybe 70 grams of frozen yogurt left, which is basically the cup and some drips. So conservation of mass says that mass cannot be created or destroyed, and using an open system, we can track it coming into the system and going out of the system, but nothing is destroyed. So to summarize, it's useful to define a system for any object that you're interested in analyzing or examining, and we think about what objects are inside or outside the system and whether or not it is an open or a closed system. And remember that the total mass in a closed system is conserved. So, like in the example of my dog and the Hai-Chu, the total mass inside that closed system never changed, even if the mass transferred within the system from one thing to another. And in open systems, we can track mass as it comes into the system and then goes out of the system again. It's also extremely important for you to know that the amount of mass in the entire universe is staying the same. So we are never going to have more mass or less mass than we do today. And when I say mass, I mean stuff, the amount of material that we have right now. So since the Big Bang, we have all the material that we're ever going to have. So the universe is essentially like a giant recycling plant, and all the atoms and all the particles are just turning into different things and moving around, but we have all the mass that we're ever going to have. And that is essentially what conservation of mass is, that mass cannot be created or destroyed.